So, let us do it perturbatively and be ready for it. Okay. This is complex set of calculation. So, I am not, we can't, well, there are some schemes to do non-perturbative, but they are complicated. So, we will do perturbative calculation, how to compute R less in terms of R naught. R naught was my original variable. Now, under coarse graining, what happens to R naught, and that will be R less. I need to derive R less and C less. Okay. So, step 1, coarse graining. This is the most difficult problem. I told you about rescaling. Rescaling is exactly like what I told before. So, coarse graining is what is the difficult aspect. Average, here I will average over in Fourier space, I will integrate those modes. Integrate, when integral is there, no? So, I integrate those modes. It will become clear in this slide. Okay, 3-4 slides. Okay, so coarse graining step 1. So, this is my free energy. So, my, as I said, my phi is phi less plus phi greater. So, this one is like phi square, phi 4, all these functions. No? So, you can just imagine that, let us imagine I have phi squared. So, it will be phi less for phi greater squared. So, I will have term which is only function of phi less. I will have formula which is function only of phi greater, and I have terms which are combination phi less phi greater. Okay. So, my free energy will be looking like 3 parts, function of phi less, function of phi greater, and mixed terms. So, these are mixed terms. Phi greater, it may be some non-zero term, but that is like it. Well, now one more thing I will assume, that phi greater is a random variable. Okay. It could be having random non-zero mean, but it is a random variable. So, phi greater equal to some average value plus fluctuation, and the fluctuation is Gaussian. Remember, we had the Gaussian fluctuation. So, exponential minus phi greater, it has this kind of x minus e to the 1 is x squared when x was with a 0 mean. So, we will use that Gaussian property, Wick's theorem, essentially to simplify this integrals as well as some of these integrals. So, this is a critical property, system is in equilibrium. So, fluctuations follow Gaussian properties. Okay. This is a cornerstone of statistical field theory or statistical physics, the fluctuations obey Gaussian distribution. Okay. So, this term will be basically can integrate out, this will be some constant, but what matters is this mixed term. Okay. And that is what we need to keep phi less and integrate out phi greater. So, in a group we need to select some people and average out and keep others. Okay. So, this term phi less, okay, this term which I am writing it here is function of, this is the linear term, right, R naught plus C naught grad phi squared, this one, and this is a nonlinear term which I wrote it before. Okay. Now, so this term is written here, this term is, we do not need to worry, it is a constant. So, free energy you can add a constant, that is not going to be mattering about the physics part. Now, the mixed part is a tricky part. Okay. So, here the nonlinear term of the mixed part. So, we have, so is phi 4, no. So, phi 4 has 2 phi's, 2 phi you keep greater, less and 2 phi greater. Okay. Or you can keep 3 phi greater and 1 phi less. So, I am just, look, I write this as phi less plus phi greater to the power 4. It is a Fourier, so I can't really write 4, I write phi k 1, then phi less k 2 plus phi greater k 2, and you do 4 of them. So, what will the terms involve? So, 4, 5 or less, which is here, right. In this product there will be 4, 5 greater, that will be where? That will be here, correct? Yes or no? When I write this product, what are the term, what do the terms look like? All 4, 5 less, or 4, 5 greater, or 2, 5 greater, 2, 5 less, or 3, 5 greater, 1, 5 less, or cubic in 5 less and 1, 5 greater. Okay. Now, this one, if I average, what will happen to this this average and this average? This is cubic in 5. So, what is the average of cubic in with the Wick's theorem? 0. These also should be 0. So, these terms give you 0. What can give you non-zero is this term, but I cannot average 5 less, I have to keep average only 5 greater. Okay. So, that is what your question is, that when you average you have to only average 5 greater, and we should basically get the blue sphere. That is what we are we want. Our system should be just the blue sphere, but probably with modified parameters. Okay. So, we need to worry about this term, this is this part, that is the most critical part, because if this term was not there, then my parameter will be remain unchanged. Okay. Here we will 5 less and 5 greater is already averaged out. We will not have combination of 5 less 5 greater. 5 less 5 greater combination which can give you non-zero is coming only here 5 in 5/4 theory. If you look, if this term was not there, only 2 of them. So, what are the combinations? 5 less 5 less, 5 less 5 less, plus 5 greater 5 greater, plus 5 less 5 greater, right. Now, this is here already, this is here, right. What about this under Wick's theorem? 0, no, one of the 5 greater, when average I will get 0. So, linear thing does not give you any non-trivial behavior. Okay. You need non-linearity to give non-trivial behavior. Okay. And 5/4, this is the most important term. Okay. So, let us write down some, I am just going to go through the algebra, I hope you will understand the steps. So, we are after this partition function z. Okay, I hope you can read from the back, and this is function of r less, c less and u less. This it happens looks like pretty tiny, but I hope you can read it. Okay. So, I want a partition function as function of r less, u less and c less. It is not r naught, c naught and u naught. Now, if I do the exponential of that, so this is the term which is original r naught, c naught, u naught, and this is a mixed term, this is a mixed term, and this is a greater term. Okay. Okay. So, I made a mistake. So, greater term is kept here, greater term is kept here. Okay. So, I had the greater term, I need to keep the greater term. Okay. So, the linear part of the greater term, because I need for averaging. In the previous term, this greater term is kept, 5 greater. Okay. So, that greater term is here, I keep it here. Okay. I apologize. So, this is the greater term, and I integrate out this 5 greater. But what is the range of 5 greater? It is starting from this sphere of lambda to lambda naught. So, this goes from lambda to lambda naught, the range of wave numbers. So, this is called K space renormalization. I am doing all this in Fourier space. Okay. So, if I take the log of this, I get with a minus sign outside, I get this term, and log of this with a minus sign. So, this object is here, it comes here. Okay. Now, I want to solve this one. This is the term. Look, without this term, r less equal to r naught. No, this is, you just focus on this and this. Without the log term, all the parameters will be unchanged. So, this is a term which is coupling phi less to phi greater, which is going to correct r naught. Okay. Now, let us go to this log term. Log term is most important. So, log term looks like that, s greater phi greater, and this is a mixed term, m is for mixed term. So, m is mixed. So, what is this integral d phi exponential s greater phi greater. So, this is the Gaussian part and any function f. So, remember we had this for Gaussian variables, this is average f, right. I wrote this property. So, this is average f. So, we write this is a average of this quantity, this is my f, okay, minus log of average of this quantity, exponential this part. Now, this exponential, in fact, is pretty complicated. No, this phi, this s is quadratic already, and I do the exponential of quadratic, I will get lots of terms, infinite number of terms, but I am going to do the truncation. This is the perturbation. So, I do a truncation, I write exponential of minus x equal to 1 minus x plus x squared by 2. I do this. So, what will I get? I get this. I just exponential I wrote like that. Now, I take log of 1 minus x minus, what is this object? Expansion of log x. So, I did two perturbation. I am basically dropping the higher order terms, I am keeping only quadratic in exponential. Now, log I will write as, this is x minus x squared by 2 and plus x squared by 2 plus x cube by 3 and like that. Okay. So, I keep only quadratic. Now, you write this as this 1 and the whole thing is x, this minus. So, this x for me, okay. This one is x with a minus sign out here. You understand, 1 minus s average minus s squared by 2. So, this is my x, this is my x. So, this is just a pure perturbation, you are dropping lots of terms, but after this operation I will get this average of s, and this is coming from x, this is basically coming from x, this one, and x squared. When I do the x square, I do not want to keep the square because s square will become 4, but I just square this one. So, I get this one, this is square this part and we will get that. Okay. So, these are 3 terms where is kept to first order in perturbation, and this is called order epsilon is first order. Okay. So, this is a word you might see in first order perturbation. Okay. Is it clear why it is called perturbation? I basically truncated the series. Now, look back, we will look at the original equation, this is what the equation looked like, right. In log term, I have these 3 terms, I ignore the rest. So, now each term has this quadratic term and quartic term, 4 terms, quartic 4. So, my left hand side, this one is here, this object is here, and this object is correction. Okay. So, what will it do? You should see the what is the global picture. This r naught less will be r naught plus whatever comes from this correction. Okay, something will come for correction that will change that will change r naught, and r naught less will be a number different than r naught. Okay. So, I need to get these corrections, and corrections are these 3 terms. Okay. So, let us compute these 3 terms. Okay, please keep in mind I need to compute this expectation value of this S mixed, alright. x mixed, the nonlinear term will contribute, the linear term is already in here. I already told linear term will give you 0 on Gaussian, nonlinear term will give you non-zero, which has 4 terms, 2 less and 2 greater. Remember I had said 2 less, 2 greater, and that is what is here. So, this is my original term in the expansion. This is for S less with R less, C less, this is S less with R naught, and this is my correction. Okay. Now, the other term which is S square minus S average squared, okay, that term does not contribute here. I am going to show you where it contributes. Okay, you have to just wait for a minute. So, let us compute this term. Now, this term was 2 phi less, phi k1, phi k2, phi k3 greater, phi k3, k4 greater. Okay. And what was the condition on k1, k2, k3? k1 plus k2 plus k3 plus k4 is 0. Okay. Now, when I average out these two, what is the condition on averaging out? By the way, these two, when I average all of them, phi less is not averaged, phi less remains as is. Coarse graining only affects the variables in the yellow shell. So, phi less should not be touched, they remain as is. So, when I average them, what is the property? That these two numbers are equal and opposite, no? You have to remember all these formulas. So, I had said that phi k and phi minus k will give you non-zero values. Yes or no? E to power I k x, e to power I k prime x average, unless k prime equal to minus k, you will get 0. So, the modes of the same amplitude, same magnitude wave numbers, but opposite sign, they give you non-zero value. So, k3 and k2, k3 and k4 must be equal and opposite. So, these two gives you 0, okay, and this is this Feynman diagram. This is that this term, and what is this? This correlation, 2-point correlation. No, I hope you have not forgotten this 2-point correlation, which is C of k. This is not small c. Okay, this is correlation function, which is same as Green's function. Okay, all that background work we did now is coming into use. So, this is the Green's function, and these two legs are here, k and k, k and minus k. This is, so k1 plus k2 will be 0. So, one of them is k, another one is minus k. Okay. So, these 2-point Green's function, after I integrate this phi greater. So, remember, I need to go back one slide. Here I have this is my original one, phi minus k, phi k less k, right? Yes or not? This is the original. This is with R naught, C naught, U naught, right? This is the original one. From this term, I am getting a term which is this loop diagram, phi k less, phi less minus k. Yes or no? I showed you this term, log term is contributing like this. So, this is the term which is changing something here. Yes or no? Right? I mean, I get additional term which is, well, this integral we give a number, it is a number, right? The integral is number, and I get a new term which is number times phi less k and phi less minus k, which is here. Even if you can't do the calculation, you should get the broad idea. That is what is correcting R naught. So, that is what is written here, R naught. Well, this term is basically this object, because this is a correlation function. Okay, this correlation function is what? 1 by k. I used to write k square plus m squared. No, Green's function for free Green's function was this, right? So, which is here r naught plus c naught k prime square. I integrate it. There is the integral involved. In the previous slide there is the integral, and basically I should get a number for this loop, and this is what is coming from after all that algebra. Now, this one is a number, no? Yeah, I get a number. Is it correcting this term c naught k squared? What I should add this number to which term, r naught or c naught? This is a number, so number should be added to a number. Had there been a term k squared, then I would have added to c naught, this stuff. So, that is why this S max is not changing c naught, is only changing r naught. Okay. This is the proof that my r less is r naught plus this number, my r has changed under coarse graining. Is it clear? Okay. So, the interaction term, well, I will do it another way, which I do it nobody, well, I did it by differential equation. I think that will probably be more easier. So, let us see. So, differential equation I will do it after this. Okay. So, this is for r naught correction, but c naught is unchanged. That is why I had written earlier that c naught less equal to c prime. Well, right now it is just going to be c naught. Okay. C naught less is c naught. C naught is unchanged because there is no term which is proportional to k squared in the correction term. Okay. So, it is only a number I get. Okay. Now, what about the other term, the square term? So, other term is s squared minus, okay, this s squared average minus s average squared, right. I had that quadratic term. Well, I put a minus, this I taken from the book, this is all taken from Copids. I should give a, okay, one more point, I should go back. This is a factor, 6. Why factor 6? This is a critical factor. This factor 6 because out of this 4, how many ways can you choose 2 greater, and so once you choose 2 greater, then the remaining will be 2 less. Okay, because only combination which gives you non-zero value is 2 greater and 2 less because of Wick's theorem. So, 4C2 will be 6, and that is why the 6 ways I can do it, and this is a property of Wick's theorem, this factor 6. Now, this term I need to get this term s squared. Okay. Now, s squared, so s squared has, so remember I have this 4 phi's, phi k1, phi k2, phi k3, phi k4. So, quartic term, quartic term 4 terms involves this, and their integral of dk1, dk2, dk3, dk4, delta of sum of k is 0. Okay. Now, what we do here is that we take 2 of these diagrams, these are Feynman diagrams. So, they will involve 8 of this, you can write here phi s1, phi s2, phi s3, phi s4. So, the integral will be 4 k's and 4 s. Okay. Now, I need finally 4 diagrams, 4 legs. Quartic term has 4 legs, no, these are 4 legs, but I combine these 2 and I want to get an object which is only 4 external legs. What should I do? I should combine them and combine these, and we combine them, I get this phi and this phi averaged, which will give me a correlation function, and this phi and this phi 4 and S3 combine, you get another correlation function. Okay. So, this is the diagram which contributes equal to that. When I do differential equation, it will become more apparent. Okay. But this diagram is here, and it has 2 vortex, 2 u's, one u is here u by 6 and u naught by 6 is here, 2 vortex. That is why you get u naught by u naught by factorial 4 6 squared, these two vertex, and this 6 is coming because I had to choose 2 less and 2 greater. So, among them 2 less here and 2 greater, which are averaged out. Greater ones are being averaged out, but you do not make a average like this. This is a, it will give you 2-point correlation, right? A 2-point Green's function, right. These are the 2 legs, which we did it already. I want 4 external legs, and 4 external legs means this is not, you do like this, 4 external legs. Okay, now this is what it is. So, we get okay, and so this is the two correlation function, one coming from here, another one coming from here, right. Correlation function is 1 by k square plus m squared. Now, m is written as r naught here, and k is written as c naught k squared. It is the same formula Green's function which we derived before, but is coming here. Now, we make an approximation that the external lex variables are small. Why? Because I am reaching, I coarse grained it, so it is a big scale. So, big scale has small wave numbers, no, larger scale means small wave number. Wave number is 1 by length. So, we will have k1 and k2 small, these two guys are going to 0. So, this is nothing but k squared. Okay. So, that is the approximation. You can do the integral, no problem, but then you have to do many variable integrals. Well, no problem is you have to do it on computer, it is a difficult integral, but this is approximation you make that k1 k2 is small. So, these two guys will become small, and so the one which we are averaging is in a yellow shell, which is large k. So, the integral we are averaging is coming from here, and so, and this is a term we do the algebra here, this 3 by 2 u naught square, okay, and this is quadratic, this multiplied by that, r naught c naught square. And what is it? It is correcting u less, the coupling term, the nonlinear coupling term u less, u naught is getting a correction from this this interaction. Well, sorry, coarse graining, not coarse graining is leading to correction to u naught, and the final u less is this plus the correction, all right. So, under coarse graining I am seeing these parameters are changing, and so we compute the effective r and u under coarse graining. So, you see r naught and u r naught and u naught have changed from the original values. Okay. So, under this operation of coarse graining I told you, this the spins are far apart and this coupling is different now, this coupling. We need to rescaling after this, but before that let me do it another way, this calculation, and I think this is easier what I am going to do now. All right. So, we will do computation with differential equation. Okay. So, this is my free energy. So, given free energy I can compute the, I can derive the differential equation by variation principle. Okay. So, that is what we used to do, dt by d phi is delta f by f, this variation, and that will, if I took that variation derivative, then I get r naught minus c naught Laplacian squared, this is by parts, and this term gives you u naught by 6 phi cube, right. I just take the derivative. So, this we done it before, but you can redo it by the same idea. Okay. Now, we are looking at equilibrium system. So, under equilibrium what happens? This is 0, right, no time dependence, and I will assume that my phi which I am coarse graining is Gaussian. So, this one, and noisy phi due to heat bath and Gaussian. So, it should be basically phi greater. Okay. So, I should say the phi greater due to heat bath, which I am averaging, I assume phi greater is Gaussian. Okay. So, we will basically solve this equation as 0. Okay. And I am going to see whether this r naught and c naught will change under coarse graining and u naught, the 3 parameters. So, instead of following a partition function and I am going to follow this equation. Okay. So, we write this in Fourier space. Okay. So, Laplacian becomes k squared minus Laplacian, and this is a nonlinear term. So, the equation which I wrote in the previous slide is this. Everybody agrees with that? The cubic term in the, by the way, please remember, I think I should write it down, is a cubic equation. So, R naught minus C naught Laplacian phi plus u naught by 6 phi cube is 0. Okay. So, this term is straightforward, this I hope everybody can do it, and this term is this phi cube is cubic, no quartic, is cubic for differential equation. It is quartic for the free energy, but it is cubic for differential equation, and this k1 plus k2 plus k3 must be equal to k, right. We did this before. Now, we make this partition of phi k is phi k less and phi k greater, and I am going to average over this phi k greater. Okay. Now, please focus on this term, nonlinear term. This is nonlinear term, no, this is, it is not linear in phi, so it is nonlinear term. So, you just substitute it here, then I will get terms all less, right, I mean cubic is all greater, or 1 less 2 greater, but there are 2 terms, right. So, I could have phi k 2 less phi greater k 1, so there are 2 more terms, right, and there is one more combination 2 phi less and 1 phi greater, but 2 more terms. Okay. So, this has how many terms cubic when I do 8 terms, and these are 8 terms, right. 2 into 2 into 2 is 8 terms, this is exactly 8 terms. So, I find differential equation to be more visualization is easy. Now, when I do the averaging, coarse graining, so remember I had to do coarse graining over phi greater, assuming phi greater to be Gaussian. So, which terms will survive? This one will remain as is. What about the second term? Is cubic, so it is 0, Wick's theorem. What about this term? 2 less and 1 greater, less you do nothing, less comes out, greater will become 0, again Wick's theorem. All less will remain less, okay, and so we need to keep this in mind. So, it turns out 3 terms of these are zeros, this is 0, well this is gone and this is gone, 2 terms are, well basically these terms are gone. This is original equation, this is what phi less, phi less, phi less. I want to form a equation with only phi less. So, remember I write down equation for phi less here, but the right hand side will involve less greater and so on. When I do the averaging, I will get the following. When I do the averaging, I get phi less plus one more term. Which one? 2 greater and 1 less. 2 greater and 1 less. We need to have only at least 2 greater, okay? 2 greater or 4 greater. So, I take it to the right hand side. I could have kept in the left and equal to 0, but I take it to the right hand side u naught by 6 and 2 greater and 1 less. And why this factor 3? Because there are 3 terms, okay. It is easy, we do not need to remember rules, there are 3 terms, so that is why factor 3 is there. So, this becomes half. Now, I need to compute this 2 greater and 1 less, okay. So, 1 less will come out, no, 1 less, nothing happens to 1 less, and greater will be, so in fact Feynman diagram will be just looking like this, 2 greater and 1 less, and this is a vortex which is u naught by 2, okay. Now, I need to compute this. So, I think you can see the answer right now, can't you? This will go out and this will become a correlation function, right. Is not it easy? to compare to Green's function and partition function and so on we needed to compute is relatively easy. So, we take this out, okay, and keep only these two and I integrate this. By the way, here is possible that I can do one more order. Okay, I am going to tell you in the next part. Okay, I can expand this and I get another higher order term. But if you do not go to that order, if I just take phi k2 out, then I will get this quadratic term, which is correlation function or Green's function. Now, what can you say about k1, k2, k3 relation? Remember, I had k equal to k1 plus k2 plus k3 vectors. So, when I do this, what will happen? K1 plus k2 is 0. So, this is gone. So, k equal to k3. So, this becomes k or k3 equal to k, which is exactly same as what is in the left hand side, right. We have r naught plus c naught k squared u k less equal to, okay. So, this part is exactly the same form as in the left hand side, we get a linear term after coarse graining. Okay. Now, we need to do something here. So, this correlation function will give a delta function k1 to k2. So, this will get out, one of them will go away. Now, I get k1 k3. So, this dk1 will be there, dk1 and okay. So, k3 will come out in a minute. Okay. Okay. So, okay, there is one more delta function, no? There is one delta function k1 plus k2 plus k3 equal to minus k. So, the two delta function, one coming from here k1 plus k2 and two delta function. So, two of them go away and we only get one delta function, one integral here. The two delta function, I did not write it here, this delta function is here, okay. Or you have to write k3 as k minus k1 minus k2 minus k, you have to write this as from here k minus k1 minus k2, then you have only two integrals. Okay. So, this is exactly same as what we got before. This is my correlation function, which I write as minus u naught by 2. This is that stuff correction, and what will it correct? This is a number. So, it is going to correct r naught, fine. Okay. Now, this is a r naught correction. Now, let us look at T2. T2 is where I am going to do one more order, but it is still first order is called, but I am correcting u naught, is a bit tricky. So, I have 2 greater and 1 less. Now, this greater in differential equation I have linear operator phi equal to some right hand side 0. Okay. Now, we write as Green's function g of k phi linear operator g of k is 1, right. So, I am going to expand this phi of k, phi greater as Green's function g of k and right hand side. So, once we have the Green's function, I said I can write down the solution in terms of Green's function, right. So, how do I solve? So, here I can solve this phi greater. So, L phi greater is right hand side, well phi greater is right hand side is minus u naught by 2 u naught by 6, sorry, minus u naught by 6 3 u's, not 3 phi's, okay. Nonlinear term I keep it in the right hand side, this is a linear operator, okay. So, what is the solution of this? If I have an equation like this, what is the solution? So, L is written as Green function's inverse, right, g of k, k. So, phi greater of k is Green's function of k and this integral this guy. Okay, we did this in the past. We write the solution in terms of Green's function. So, I am going to write one of these phi greater in terms of what I wrote here. Okay. So, one sorry, so this is less. So, one less, this less is kept here. Okay, this is the less part. One greater part I write as Green's function, this is Green's function, and the Green's function will give you this Green's function. So, if pay attention, this Green's function and 3 u's, one u is here, one u is here, another u is here, 3 u's, no. Okay. So, 3 u's I write as a okay. So, one greater is here and I write one greater here. So, for this part I will keep 2 less and 1 greater. I will not keep 2 greater and 1 less, but I will keep 2 less and 1 greater. I am not doing averaging right now, averaging will be done later. So, here I will have 2 less and 1 greater, and this 1 greater, this greater, this greater, this greater is coming here and this greater will combine. Okay. So, this is a Feynman diagram way to represent it. This greater is going to combine with this greater, okay, and we will get a correlation function from here. And Green's function is same as correlation function. So, we get the 2 correlation functions. Is it clear to everyone? So, express one of this, expand this u greater is a Green's function and 3 legs, 3 legs, 1 leg, 1 leg, 1 leg, but 2 legs are u less, phi less, and third leg is phi greater, and that phi greater, this phi greater is going to combine with this greater, because I need a non-zero value, otherwise they will get 0. So, I need 2 graters. So, 1 greater from the new one and 1 greater remaining from the old one, combine them and you get correlation function here. So, that this integral will be 3 L1s. I write L1, L2, L3 for coming from here, and this is original dk1, dk2, dk3. This is a delta function which I am not writing here, and so one Green's function, this Green's function is here. 2 L's, the 3 L's, 3 L, 1 L1, 1 L3. These are 2 less guys. One greater guy which is coming from here, greater guy, and one greater which is here, this greater, and one less is, this is one less. Okay. I need 3 less. Remember the original of in the left hand side I have 3 phi less, no. I want my new equation to look exactly like old equation, except that I am only allowed to change the parameters. So, this is great. Why is it great? Because I have one less, another less, another less, 3 less. Okay. So, this is multiplication. So, there is a u naught, this vortex, and this vortex is this vortex. Vortex is this term, okay, this front of the legs. In the nonlinear term there is a factor in front, that is called vortex. So, you write as these 3 less, which is the circle ones are kept here, and the integral ones whatever we need to integrate we write as gk1, and these 2 greater, these 2 greater will combine to give you ck2. k2 plus L2 is 0. Okay. And so, we got all this stuff. Okay. So, now if you do the algebra right, so we have to follow this condition, no, this function, and k2 plus L2 is 0 coming from here, and what do you get from here? What is the condition from here? This was gk right, this is gk1. So, k1 variable, k1 wave number is leading to 3 wave numbers. So, what should be the condition on the wave number? k1 equal to L1 plus L2 plus L3, right, coming from here. These are the new babies. Okay. So, the wave number must be conserved. This is the momentum conservation. So, this 1 and then we have k1 plus k2 plus k3 equal to k. You put all these conditions, then you get some contraction delta functions, and we get this. This is collapsing into that. Okay. So, this is this part is like nice before, but you get integral. We have one more condition. We again assume that this external legs are small. Okay. So, that means L1, K3 and L3 are small, and that makes it this condition comes exactly like what this is very it is similar to the calculation for the in terms of partition function, but I find it easier, at least I am comfortable with this. Okay. And this is what we are getting as a correction. I am sorry, this is collapsed into this PPT conversion, and the prefactor u naught square by 4. This is not correction because I need to write a equation which is same looking, similar looking as the original equation. So, let us now put it together. Okay. Let us now put it together. So, this was our original equation, okay, without the nonlinear term, without the right hand side. So, I take the right hand side to the left. So, the first term which was u naught by 2, I have taken it to the left. Okay, this is the first linear term, this is correcting R naught, okay, this is R naught correction, and the other term which is coming from this diagram, which was this diagram. Well, I mean basically I have 3 legs. I made the diagram before, no. So, the well I basically I wrote the diagram like this. So, it was diagram like that. My diagrams are different than what we do for Green's function. Green's function has 4 legs, but since I am doing with differential equation I have 3 legs for the nonlinear term. So, this is the term and this we get the prefactor is minus u naught square by 4. I have taken it to the left. So, what do I get? So, now I need to combine them together. So, I will add, where should I add this term? I should add it here, no? Where should I add this term? I should add to the nonlinear term. L1, L3, K3 are dummy variables. So, I can rewrite them L1 and L3 as K1 and K2, right. So, these are the 2 corrections. So, exactly same as before. So, my new equation is looking like this, except my R less is equal to R naught plus this is delta R naught, this object is delta R naught, this one, okay, this object delta R naught, and u naught, remember this is u naught by 6 here. So, I need to worry about that u naught by 6, already prefactor is there. So, u naught less by 6 equal to u naught by 6 and da 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 da, and that gives you equation for u naught less is this, which is identical equation as what we got before. Okay. So, these are the corrections which we got from coarse graining. Now, we still need to do rescaling. So, whatever, so I did this derivation before. So, I get R less to get R prime. So, what we are doing is right now I had the blue sphere inside and yellow sphere outside. So, now you need to make the blue sphere go to the same size as the big sphere. So, that is by factor B. So, that operation involves this. So, for the big sphere my parameter will be R prime, not R less. So, I just need to multiply by R squared for R prime, and for u prime I need to multiply by b to the power 4 minus d. I derived it before. So, this is my R prime. You ignore ZB, okay. So, ZB is functional renormalization which we right now we do not need to get there. ZB is 1 for you, okay. I cut it from that book by Kopitz, and u prime is this. So, this is the transformation of u naught and R naught under RG, which has 2 steps, one is coarse graining, other one is rescaling. Okay. Now, it has, you see that it has changed. Now, so that is it. Okay, so we will start from here and we will see what is a fixed point for this transformation. So, we are looking for a scale invariant system. It turns out under near phase transition r prime is same as r naught and u prime is, so we will get a fixed point. Okay. So, we need to get, and from that we will derive the properties of phase transition. So, that we will do in the next class.